let's see. So we've got this. We're looking for the total flow rate in this previous exercise. And let's see, in that previous exercise. Okay, so we've got this function s of x comma y. And let's see, the canal is 50 feet wide, 10 feet deep. So x and y go from 0 to 50 and 10 respectively. Okay, so we have integral dx from 0 to 50 and integral dy from 0 to 10. And the integrand is 11 minus y over 100 plus x minus 25 quantity squared. Okay. All right. So this is really just a couple of single variable calculus problems at this point, right? By the way, did I get this integral right?
Yeah.
Okay, yeah. Okay, so yeah. So you got to be careful about, again, now what variables are playing which roles. And so the first observation I want to make is this denominator, it's constant, at least as far as the y integral is concerned. And so that can just go right outside of the y integral. Now it can't go outside of the x integral, right? Okay. All right. So that gives us then. Good. So let's see here. We've got 1 over 100 plus x minus 25 squared. And then now we've got an integral of 11 minus y dy. So let's go ahead and do that integral. So I have 11y minus 1/2 y squared. And now we're going from y equals 0 to y equals 10. And that is... I just got to plug in some numbers here. Now, obviously, when you plug in y equals 0, you get 0. And with 10, you get 110 minus 50. So it gives you 60. Okay, so we have 60 over... Okay. Right. Okay, now what?
Yeah, this integration was kind of hard to do with that integration.
Yeah, absolutely. So there's a nice little trick to remember here. And so this, did y'all take single variable here?
I tried to do partial fractions, but that kind of didn't work.
Yeah, that's not going to work super well. You're going to get complex roots and stuff. The trick here is to use trig substitution. Y'all remember trig substitutions? Yeah.
Okay.
So now there's different points of view you can take on how to motivate what exactly the right trig substitution is. Let me show you the way I do it, because my way does not rely on really remembering anything, which is great because I can't remember anything. Okay. Yeah, come on in. So here's what I do. I look at what we've got. I'm going to do this here in. Oh yeah, sure. You can just set it on top of that stack right there. Perfect. Thank you. Okay. So look at what we have and think about, the fact when I make a substitution, I can change certain things, and I could just say I want this to be, like some function of x. I can turn into some function of u or whatever, right? But I can't change that 100. That's going to be 100. I can't say let 100 equal 5. No fair, right? So when I say, what do I want this denominator to turn into, I got to keep that 100 right there. But this x minus 25 quantity squared, I could really turn that into something. And so I'm going to say what I would really like that to turn into is 100 tan theta squared. Now let me tell you my reasoning. I want this 100 because that way I can factor out the 100. Okay. Right? And that then leaves me with just 1 plus tan squared. And the reason I want 1 plus tan squared is because that's secant squared. Does that sound familiar? Yeah. So let's do that. Now, in order for me to get my wish, in order for this to equal to that, I've specifically got to let that equal to that. So I need for x minus 25 squared to equal to 100 tan squared theta, which I can arrange if I were to let x minus 25 equal to 10 tan theta. Right? That would certainly arrange what I want. Right? So this is the formula that I'm going to use. Now, if you want to solve x equals whatever, you can. It ends up we're not going to need to do that. Right? I just need this equation relating these two things. And now I am going to need to eventually know what dx is. So let me take a differential of both sides here, and I get dx equals 10 secant squared theta d theta. Does all this look kind of vaguely familiar? Did they do this? Yeah. Okay. All right. Okay. So I'm going to say let's make this substitution, and having done so, my integral turns into, well, 60 is still the numerator. The denominator, let's not forget, the whole point of this substitution was so that this would turn into that. And the whole point of that was so that I could rewrite that as 100 1 plus tan squared. Right? Right, okay, then let's see now, what about the dx? Well, dx, oops. Dx is that. It's 10 secant squared theta d theta. Let's write that down. Okay. All right, and now begins a bunch of arithmetic. Or algebra. So, okay. So first observation I'll make is that that 10 and that 10 cancel that 100. Then let me observe that secant squared theta is 1 plus tan squared theta. Yeah. And so all that's left is, and this is actually kind of awesome, is I have integral of 6 d theta, which is nice. So that gives me 6 theta plus c. If I don't need the plus c, I'm going to be plugging in bounds in a minute. Okay. By the way, let me point out that I have been deliberately sloppy about one thing. You'll notice that I did not put anything there or there. And the reason why is because, well, it's not 0 and 50.
Yeah.
And so, well, I guess I could figure out what those numbers are, but I don't really need them, because as soon as I get this antiderivative done, I'm going to convert back into trig and into the X language anyway. So I just leave them blank. I guess you could put a dot and a dot just to acknowledge that something needs to go. Anyway, okay. So 6 theta. So what is theta? Well, you could solve for theta here. So theta is arctan of x minus 25 over 10. And that is what you plug in 0 to 50. Cool. Yeah, and now you do some plugging in, and let's see here, you get, well, anyway, you get some numbers. Yeah, right.
That makes sense.
Yeah. You okay with this? Okay. All right.